Welcome back, everybody. Let's go ahead and finish out our unit here on the motion of the ocean, and we'll start by talking about tides. We have this twice daily rise and fall of sea level. So we have our sea level high point, called the high tide, our sea level low point, called the low tide, and the difference between them is the tidal range. Typically, these are going to be just maybe 6 to 10 feet, but there are certain places in the world where tides can be as much as 16 meters or even 50 feet or more. So these huge, almost 60-foot tides are going to be in the Bay of Fundy. It's going to be here between New Brunswick and Nova Scotia in Canada, very, very close to Maine. Right? So we have an increased tidal range as you get further into the bay. What would this actually look like? Well, we have some photos here, right? So this is what it looks like during low tide. People can go and walk around this whole landscape. And in high tide, the water comes way up to the point where people can actually get in boats and kayak around. Right? And you can actually see a more extreme example here. So we have high tide on the left and the low tide on the right, a giant difference between what it looks like at the high and low tide here. Now, we'll ask the question here of what causes these tides. Well, we have to think about the gravitational pulling of the moon and the sun, which varies over time, right? The sun and the moon have mass, they have gravity, and so they're going to pull and stretch out the body of water that is all the oceans on Earth, right? You might think of it as one big water body here instead of separate oceans. And we're going to have two different kinds of tides that we'll talk about. We have cases where the sun and the moon are pulling in the same sort of direction. In this case, they're pulling in exactly the same direction, but if the moon were over on the opposite side, then we would be pulling horizontally as well, and we would get a spring tide, right? These are going to be aligned. So again, it works here with the moon and the sun on the same side, but if we took the moon and put it on the other side, we would be squeezing apart like this, and we would have the same pattern, something called a spring tide. We have high tide over here that's being pulled, high tide over here, low tides here and here. And as the moon orbits, it might get to a point like this. Now we have the moon pulling in one direction, pulling vertically here, and we have the sun pulling in another direction. And the result of this is that they don't add up. In fact, they're going to pull in totally separate directions, so the high tides are not quite as high as they were for the spring tide, and the low tides are not quite as low as they were for the spring tide whenever everything was aligned. And we'll call this a neap tide. So whenever the sun and the moon pull along the same axis, even if it's not in the same direction, so it could be like this, and it could be like this, we're going to have a spring tide. We have high tides and low tides, a big difference in the two, big variation between them. Nothing to do with the season of spring. It's from this phrase of springing forth for the tide. It's going to occur twice each lunar month, which is about the same as a normal month based on the moon. So we have situations like this. We would have a new moon where we have the Earth and the moon and the sun, and it would also happen with a full moon if the moon was over here on the opposite side. We also have these neap tides. We have low highs and high lows, so a smaller range overall between the highs and the lows. I have no idea where the word neap comes from. You can still ask me if you'd like. This is going to occur whenever we have our first and third quarter of the moon. So the moon is going to look half full. Right? We're sitting here on Earth. We look at the moon. We have half of it with sunlight and half of it which is dark. And over here, it would be the same thing. The idea is that the sun and the moon are not pulling along the same axis. One of them is pulling this way, one of them is pulling the other way, so they do not add up, they do not align at all, and so we have a more subdued tidal range. And before we can go any further, we have to do a little bit of review on the phases of the moon. So we start off with a new moon. This point, the moon is not receiving any sunlight at all. You might imagine that the moon is right here, and we're looking at it on Earth. Well, the sun is on the opposite side, so the opposite side is lit up, but right here, the side that we can see gets no sunlight at all. And as it starts to travel around the Earth, more and more of it starts to get sunlight. So we would have our waxing is a growing crescent. We'd have our first quarter here, where the right side of it is lit up. We would have our waxing gibbous, waxing is in growing, gibbous whenever it's 3/4, then our full moon, whenever it has reached the other side entirely. So we're standing here on Earth, we look at it, we notice that it gets all this sunlight from the sun. The Earth would not be in the way of this, not usually. And then it goes through the opposite cycle. So we have waning, as in getting smaller, gibbous, third quarter, waning crescent, and then finally a new moon. Again, for every lunar cycle, be about 28 days. So how do these phases of the moon and the tides interact? So to review, this is what we might see if we have spring tides and neap tides on a graph, right? So we have water level going up or down, so high tide and low tide. we notice that with the spring tide, the highs are higher, the lows are lower. The neap tide, each one is a little bit more subdued, right? So we have a bigger tidal range for the spring tide, smaller tidal range for the neap tide, and we're traveling forward in time here, and the same is true of this graph below, right? So we have water level, and we have time. So looking at this graph, we might be able to identify certain spring tides and neap tides. For example, this looks like a spring tide here, high highs and low lows, and this looks like a neap tide over here, right? So we have our spring tide and we have our neap tide, but there's sort of a problem here. Why does this spring tide not really look the same as the one over here? In fact, this spring tide looks like the highs are super high and the lows are super low. What is the difference? To answer this question, we have to look at the actual orbit of the moon. Now, it's very close to being circular, but not quite. You notice there's a bit of difference here, right? Whenever the moon comes through this part of the orbit, it is a little bit closer to the Earth, something called the perigee. As opposed to over here, it's a little bit further from the Earth, we have the apogee. And if you were on the Earth, this is what you would see at these two moments, right? We have a full moon for the perigee. Perigee is going to be closer, so we would have this really, really big full moon that you could look at and see from right here. On the other hand, you would have an apogee, right? So the moon is further, it's going to look smaller and a little bit less bright, something called a micromoon here. And the way that this relates to the tides is, well, whenever you have a perigee, the gravitational influence of the moon is going to be stronger. In other words, tides are going to be more extreme during the perigee and less extreme during the apogee. And this explains why one of the spring tides is a little stronger and the other is a little bit weaker. The stronger spring tide must have occurred during the perigee. So this pattern that I've talked about here with the perigee and the apogee with the moon, this is going to repeat every lunar cycle. It'll be about 28 days. There is also this bigger annual cycle to the tides. So the Earth is going to be closer to the sun during a certain period, closer to January, going to be further from the sun, closer to July. And the point where it's closest is going to be the perihelion, like perigee. The point where it is furthest is the aphelion, like apogee. Actually, it's a pretty substantial difference here in absolute terms, about 5 million kilometers. So, during these perihelion times, where the Earth is closer to the sun, it's going to have a greater influence on the tides, and you get a greater tidal range as a result. When it is further from the sun, it's going to have a subdued effect on tidal range. We get a lower tidal range as a result. Okay, so let's put it all together here. Now, we're going to come back to this graph. You remember looking at this, right? We have our water levels and tidal ranges. We're moving forward in time. We looked, we identified a spring tide here, a neap tide here in the middle, and then another spring tide, and we said, well, wait a second, this spring tide looks more extreme than this one. Why would that be? And now, because we know about the perigee, the apogee, we have our answer. So here we are in November, right, as we're orbiting around the sun, and we can look and we can say, okay, this is going to be our full moon, this is going to be our new moon, this is going to be our apogee, moon is further, this is going to be our perigee, moon is closer. So what we would expect to see is weaker tides over here whenever we have our full moon at the apogee, stronger tides over here when we have our new moon at the perigee. How do we put this all together? Well, we look, okay, so here's mid-November, here we have early December as we're moving through, and we can actually match this up, right? So this is going to be our full moon at the 19th of November, which is at the apogee. So because it's at the apogee, the tide is going to be weaker here, and we are going to get a stronger tide with our new moon over in December as we get closer to the perigee, closer to December 4th. That is why we have a stronger spring tide over here than we had in the middle of November. So for our final component, we'll talk about waves. Waves are primarily going to be driven by wind. You have wind at the surface, which pushes the water and actually can cause substantial motion of it. We have wind, which transfers energy to our wave, which then transfers energy onto the coast in turn. Importantly here, the wave energy is going to be proportional to the square of the wave height. What does that mean? Well, to have a wave that is a little bit taller takes a ton more energy. That's what that means. It provides somewhat of a limit on the size that waves can be. It's the reason why you don't very often or ever see waves that are going to be hundreds and hundreds of feet tall, because you would need an incredible amount of energy to do this. These are responsible for a lot of the coastal landforms, which we will look for in the next section, and also do a lot of transporting sand and sediment. We'll look at that process as well. Now, what is the actual mechanism involved? Why does water form a wave? Why doesn't it just push along and hit the shore? So, we have our coastline, and as you get closer to land, the water depth decreases. As your water depth decreases, the waves start to get slower. So then you have faster moving waves here and slower moving waves as you get closer. And as a result, what starts to happen is the waves in back start to push on the ones in front of it. They build up until they finally move over themselves and collapse. They roll up on the shore and roll back. And this is how we get waves which are continuously reworking the coast and changing it. Now, we can actually model the coastline in this way. And don't worry too much about the details here. We have these lines coming across like parallel to the shore. We might call these wave fronts, and the actual waves themselves are going to travel perpendicular to the wave fronts. And the effect of this is that a lot of waves are going to point in and hit parts of the land that are more exposed to the ocean, as you would expect. So here we have our headland jutting out, going to get a lot of wave action, a lot of erosion as a result, as opposed to places that are further inland, places like bays, going to be lower wave energy, tend to be relatively sheltered, tend to be sites of sediment deposition, as opposed to the eroding headland. Okay, so that is it for our section here on the motion of the ocean, waves and currents and tides. For our final section, now we finally get to talk about the results of this. If you go to the coast, you see all these different rock formations. What do these mean? This is going to be all in our section on coastal landforms.